So here is problem 10, and I've written this out in an ICE table the way you're going to need to first think about this until you then see that this is going to be, I don't know if it's a cubic or a quartic, but it's a difficult algebraic problem to solve, and that should make a light go off, because I told you I'm not going to ask you to do anything above a quadratic. So I think you should do this every time anyway. First, look at the magnitude of the equilibrium constant. And in this case, it is a huge equilibrium constant. It is 10 to the 20th in magnitude. And that means we have to have a 1 with 20 zeros more product than we have to have reactant. That means this is the old style. This isn't an equilibrium. It's going all the way to make products. And that means there's no way you can equal that equilibrium concentration, that equilibrium constant, and still have effectively any reactant around. And this asks, what will the concentration of the reactant be? And there's two very large numbers, and that is physically impossible. There's one, okay, it's moderate, but even if that final concentration in equilibrium is 0.01 molar, as one of the options is, that means we'd have to have 10 to the 20th times 0.01 molar on top. You can't do it. So you don't have to do any calculations, is what I'm saying. And the only possible answer here has to be that one, the one with a very small reactants remaining, because that's what the equilibrium constant tells you. So no calculation here. Just always start by looking at the magnitude of the equilibrium constant. Because remember, if it's huge like this, that means it's going to completion. The other thing we want to know is it small? And if it's small, we can use that x is small approximation. And only when we have these equilibrium constants that range between 100 and 100th, or 1,000 and 1,000th, do we have to start, doing quadratic solutions and that sort of thing. So always look at that first, and this one should lead you directly to the answer. Okay, for problem 11, it's a Le Chatelet problem. So it's telling you the follow reaction is exothermic, and that means, to start with here, the heat, it's a product. And then we're going to just do stresses to this, right? We're going to raise the temperature. Well, Le Chatelet says that no matter what the stress is, the system shifts to remove that stress. So if it's increasing the temperature, it's going to move to the left to cause temperature to be consumed. Okay, that's one correct answer. And then that rules out the bottom answer, none of the above. And it also, then the next answer is all of the above. Okay, so we either have one correct answer, we can't have two correct answers, we have to have three correct answers, or one. So let's look at the next one. If I just increase the volume. So I'm in a container or piston, and I raise the piston, it increases the volume. Overall, the pressure is going to drop. And remember, what happens is that the system moves in a direction to increase the number of moles of gas. And so there's 2 moles on the right, 3 moles on the left. That means it's going to shift to the left to reduce that. That's another possible answer. So the only possible choice here is all of the above. Okay. We only have a minute left in this video, so I am going to go ahead and work out the algebra, and then I'll talk you through it. And so I just jumped ahead and filled in these steps. So what I did here is I just rewrote this after doing my squaring, and then I divided both sides by that to get this value, and then I simplified to solve for x, and that's what the question asks. What is the equilibrium concentration of CO2? And that number turns out to be this one, and that is our answer.